In this video, we're going to look at the reactions of phenol. Now, you'll remember from benzene that the delocalized ring structure reduces the reactivity of benzene. So because that region of electrons in the pi system is not very dense, it's unable to polarize electrophiles sufficiently in order for benzene to undergo addition reactions. Now what we're going to do is have a look at phenol and have a look to see why phenols are more reactive than benzene on its own. Now, what we need to do is have a look at some lone pairs of electrons here on the oxygen atom of the OH group. Now, as I was saying, in benzene, there's a delocalized ring system. This pi system above and below the plane of the carbon atoms is spread out and the density of the electrons is not very high. Now in phenol, one of these lone pairs of electrons actually forms part of this pi system. So here's the pi system, and then it starts to incorporate a lone pair of electrons in here. What that does is it increases the density of electrons in that pi system. Now the increased density of electrons in that pi system enables phenol to polarize bromine. Now because the bromine is now polarized, this molecule of phenol can undergo a substitution reaction. It's still a substitution, not an addition reaction. It can still undergo a substitution reaction, but it will do this under room temperature and pressure rather than needing a catalyst or anything like that to happen. Now there's another really important thing that this impacts upon. Now because the lone pair here is drawn in towards the ring and delocalizes and becomes part of the ring system, the effect is the oxygen is also drawing electrons towards itself because it's more electronegative than the hydrogen. The impact that has is it weakens this bond here between the oxygen and the hydrogen, and that makes phenol ever so slightly acidic. Now it's a weak acid because it only partially dissociates, and that's shown here by the equilibrium sign. So if you dissolve phenol in water, a slightly acidic solution is going to form. Now the equilibrium is lying towards the left, so this is a weak acid. But that's important because it explains a couple of the reactions we're about to look at in terms of phenols. So the two key things that we've looked at so far, the lone pair of electrons delocalizes into the ring system, into the pi system, making this pi system more dense. This is going to make phenol more susceptible to attack by electrophiles. Also, it's going to make phenol slightly acidic, and therefore it should be able to undergo acid-base reactions. So we'll have a look at a couple of the reactions here of two phenol molecules that I've drawn. So the first reaction we'll look at is if we added a piece of metal, a reactive metal such as sodium, to phenol. Now when you add metals to acids, you get some effervescence because hydrogen is produced. You also produce a salt from the reaction as well. So the salt produced is sodium phenoxide, and some effervescence produces hydrogen gas here. You can test for the hydrogen gas by collecting some in a test tube, using a lit splint. If you light it, you should get the squeaky pop as a result. Another reaction that phenol will undergo is with strong bases such as sodium hydroxide. The products, first of all, the salt is the same, so you get sodium phenoxide again, and then you produce water from the reaction in an acid plus base is salt plus water reaction. Another reaction that's really important here is to consider is the reaction with sodium hydrogen carbonate. Now, sodium hydrogen carbonate is used to test for the presence of a carboxylic acid group. Now, phenols, we've said, are slightly acidic. Now, the important thing here is phenol does not react with sodium hydrogen carbonate in the same way that carboxylic acids do. That's important because it's a test to tell the difference between having a carboxylic acid or a phenol. Phenols just simply aren't acidic enough to be able to react with it. There are two more important reactions that we need to look at in terms of phenols. So I've mentioned about bromine reacting with phenol at room temperature and pressure. Remember, the lone pair of electrons forms part of the delocalized ring. The delocalized ring is now more dense, and therefore it's able to polarise the bromine molecule at room temperature without a catalyst. The effect of this reaction then is a substitution will take place, electrophilic substitution will happen, and 3 of the bromine molecules will attach on carbon 2, carbon 4, and carbon 6. So the product of this reaction is 2, 4, 6 tribromo phenol. The other product of the reaction is hydrogen bromide, and therefore we just need to make sure we've balanced. We need 6 bromines on this side, and we need to ensure that we've got 6 bromines involved in this side as well. Now the observation you'll get from this, because bromine is orange, we no longer have bromine on this side. That will turn colourless, but afterwards the 2,4,6 tribromophenol will precipitate out and a white precipitate will be observed. So this is a test for phenol, because phenol, unlike benzene, will react with bromine at room temperature because of the more dense pi system. A final reaction to look at is the reaction with nitric acid. So, unlike benzene, phenol can react with dilute nitric acid. A catalyst is not required for the reaction, and there are 2 potential products that we could make out of this reaction. So our electrophilic substitution could occur at one of 2 carbons. We can either make 2 nitrophenol, so we've got 2 nitrophenol here, or we could make 4 nitrophenol, and we'll get a mixture of these different products from this reaction. So 4 nitrophenol. The other product from this reaction is water. That's our waste product here. So these are the 2 organic molecules that we could produce. You'll need to look at the directing effect of groups, which we'll look at in a later video as to why it's either 2 or 4 here, or why we've gone to 2, 4 and 6 in this particular reaction here. So that's a quick video looking at the different reactions of phenol. Make sure you go back right from the beginning, understand what's happening in terms of that lone pair of electrons forming part of that ring system. That explains why phenols are slightly acidic. It also explains why phenols are more reactive than benzene. And then you should be able to write equations for the reactions between phenols, sodium, phenols and sodium hydroxide, and the reactions between phenols, benzene, and phenols and nitric acid. Thanks for watching. If you like the video, please make sure that you give it a good like. Also, if you could share these videos, that would be absolutely fantastic.